All right, so let's say that we have a circuit like this. I'm going to say V cosine omega t with a resistor, just a simple resistor connected to it. And I'm going to give this particular values. I'm going to call this guy 3 cosine omega t, and this guy 2 ohms. And so the frequency I'm going to give this guy is 2 pi times 0.5 radians per second. In other words, F equals 0.5 hertz. So 1 period is 1 over 0.5 or 2 seconds. Okay? So remember that I can describe this circuit a couple of ways. I can write this guy as 3 cosine 2 pi 0.5 t, or I can write this as the real part of 3 e to the j 0 degrees e to the j 2 pi 0.5 t, like that. Okay? Now, remember, if I wanted to expand that, I can always say real part of 3 e to the j theta, where theta is equal to 0 degrees plus 2 pi 0.5 t, right? So real part of 3, remember e to the j theta is cosine theta plus j times 3 sine of theta. So the real part is this part that doesn't have the j. So that's 3 cosine theta, plug back in what theta is, and I could just write that as 2 pi times 0.5 t, like that. Okay? All right, so remembering that, we call this thing here our phasor. Okay? So here's my 2 ohms. So I'm going to have an I of t here. If I try to solve this thing, I should end up seeing that in this particular case, I of t is going to be 3 volts divided by 2 ohms cosine 2 pi 0.5 t. Okay? So in other words, 1.5 times cosine 2.5 t. Now, if I draw that in the phasor domain, I do this simply in terms of phasors. And I say in the phasor domain, or frequency domain, I say that's V underline. Here's I underline. I write this guy as 3 e to the j 0 degrees. And I say this is 2 ohms. Okay? So I can say that I is simply equal to, by Ohm's law, V divided by 2, right? Or 1.5 e to the j 0 degrees. So the way I write that is I say in a complex plane, I can say my voltage vector is here, and my current vector is half of that, okay? That's how I express that. Now I'm going to move this guy over a little bit, and I want to look in parallel at this little program right here, okay? So this was what we drew as our phasor representation over here, okay? Now I'm going to try to draw the same thing here. So in this little MATLAB program that I've got right here, what I've written is that the voltage has a magnitude of 3. So down here in the corner, voltage is a magnitude of 3, has a phase of 0 degrees. So this is our phasor representation, okay? And I've said I've got an impedance with a magnitude of 2 and an angle of 0. That's equal to R equal to 2. And I've set the frequency to 0.5 hertz, okay? So notice what I can see about this. The red is the voltage, the blue is the current. So one thing I see right off the bat is the red voltage looks like a cosine function, okay? And the period is 2 seconds, just like we said. So here's the beginning of a period. Here's the end of the period at t equal to 2. In other words, this guy traversed 360 degrees, or 2 pi radians, in one period, okay? And then another 360 degrees, or 2 pi radians, between 4 seconds and 2 seconds, and then between 4 and 6, and then between 6 and 8, and then 8 and 10. So it looks like we went through 5 periods in 10 seconds, which makes sense for a period of 2, okay? Now, up here, I'm showing what I call my static phasors, okay? This diagram in the upper left is the same as the one that I drew previously, okay? Now, what I'm showing here in the upper right is what I call the rotating phasor representation. In other words, what that guy is going to show me when I run this thing, I'm not running it yet, is it's going to show me a couple of things. It's going to basically plot v e to the j omega t, where my omega is 2 pi. Let me keep it general for a minute. E to the j omega t, with v equal to 3 e to the j 0 degrees, and omega equal to 2 pi times 0.5, like that, okay? So I'm going to see, for the voltage at least, right? I'm going to see 3 e to the j 0 degrees times e to the j 2 pi times 0.5 t. Now what is that going to look like, okay? Well, it's going to, so essentially what I'm going to see is this will be the stationary phasor that's going to show me what we have just been calling the phasor. So this is going to be in the upper left. And then this guy is going to change as a function of time. So what I'm ultimately going to see, this combined thing, is what I'm going to show as my rotating phasor. Okay? My rotating phasor. So this is going to be in the upper right. Okay? Like that. So let me go ahead. Here's how I run this thing. Okay? I hit calculate I, and so notice that the vectors start moving and time advances. So as time advances, the time domain waveforms move and these vectors move, but the stationary vector doesn't, right? The stationary vector is just the phasor 3 e to the j 0. So let me run that again, except I'm going to pause it. Okay? So there I paused it right at time t equal to 1. Okay? Now at t equal to 1, in the upper right, what I have is my rotating phasor up in the upper right. So that is v e to the j omega t. And specifically in this particular case, it's 3 e to the j 0 degrees times e to the j 2 pi 0.5 t. Now in this particular case, since I evaluated at time t equal to 1 second, I put in the 1. Okay. So what does that equal to? So the way I evaluate that, right, as I say, it's 3 e to the j. If you go through and combine these things, it's actually not hard to see that this is 3 e to the j pi. And if I expand that guy out in terms of the Euler identity, 3 cosine pi plus j sine pi, like that, it becomes -3. Okay. So notice, that's what I see in this rotating vector case, right? I see that this guy is sitting at -3. So the red is pointing, so he's got no imaginary part, and he's got a real part of -3. Okay. Similarly, if I say to myself, well, what's the real part of that thing? Well, the real part of this guy is 3 e to the j 0 degrees, e to the j 2 pi 0.5 times 1, like that, right? If I go to my calculator and try to calculate this guy, right? I mean, I can see it from above, right? I don't even need to go to my calculator. I see that that's equal to -3, okay? So the real part of this guy is -3. I also see that the voltage, the original voltage at time t equal to 1 is 3 cosine 2 pi 0.5 times 1. I go to my calculator and I compute that. I can't compute it in MATLAB, unfortunately, but I can calculate it separately in my calculator. I see that I get -3. Okay, so let's look at a couple of things here. So for this rotating vector, I see that it's basically pointed over here with a real part of -3, and I see that the time domain vector is also at -3. Okay, so let me continue to run it a little bit, and let me pause it somewhere a little bit more random. Okay, so at this particular spot, I'm basically looking at t equal to 2.4. Okay. And we know that v of t is 3 cosine 2 pi 0.5 t. And we know that that's also the real part of 3 e to the j 0 degrees, e to the j 2 pi times 0.5 times t. Okay? Now, if I evaluate that at 1, or sorry, not at 1 in this case. In this case, it's 2.4 seconds. Okay. At 2.4 seconds, I see I have 3 cosine 2 pi 0.5 times 2.4. Right? If I put that into my calculator, I get 0.927. Okay. So if I look at that, look at the red guy, right? So what I can see is that at time 2.4, right? So basically I'm right now at time t equal to 2.4, what it says right here. Time t equal to 2.4, it looks like my red value is just below 1, right about 0.927. You can also see that the real part of the red vector right there is sitting just below 1, right? So there's 0, here's 1, so he's just below 1. If I continue it, right? Here, notice at any given point, right? Here's my time domain waveform, which is cosine. And at this particular point in time, 3.9, I can go and calculate it. I'm basically just before the end of the period. So I'm right below 3. And the real part of this red vector is just below 3. So we can kind of see a clear relationship that exists between those two things. Okay? So that's kind of important. Notice that the static phasor piece, just that 3 e to the j 0, right, that never rotates. And the reason we use this, right, the reason we use this is because essentially if you look at what's going on between the phasors as they move, is there relationships between each other at any given time. So I can pause this guy at any given point. Those rotating phasors are essentially always having the same phase relationship with each other. So the reason we draw that whole static phasor thing is because time doesn't matter, right? For us to be able to understand what the time domain waveforms is, the only things that we need to know are how the amplitudes relate and how the phases relate. So notice that the phase relationships and the amplitude relationships here never change, right? As time advances, this guy just keeps rotating, but the phase relationships between the red voltage and the blue current never changes. All right, so I stop there. Now let's say instead that my circuit had 3 sine 2 pi 0.5 t as my input. Okay. And let's say I still had that 2 ohms like that. Now, if that's the case, we said that whenever I have sine, I write 3 sine 2 pi 0.5 t as the real part of 3, and I always bring in a minus j, e to the j 2 pi 0.5 t, like that. And I said this minus j represents a rotation by negative 90 degrees. So I write this as real 3, remember, so minus j is equal to e to the minus j 90 degrees. So this becomes 3 e to the minus j 90 degrees times e to the j 2 pi 0.5 t. Okay? This guy here is now my V phasor. Okay? So if I draw for this particular case, right, if I say, well, what's the current phasor? The current phasor is the voltage phasor divided by 3. So I say 3, oh sorry, divided by 2, right? 2 because my resistance is 2 ohm. 2 if I do that math, I see that I get 1.5 e to the minus j 90 degrees, okay? So a couple of things we see from that analysis. If I draw the phasor diagram, I see that the voltage is 3 minus 3j, like that. This is our V, and our I would be half of that. Now, if I were to convert this back into the time domain, right, I would see that this is 1.5. So again, by taking the real part of I, e to the j 2 pi 0.5 t, if I take that, right, I would get 1.5 cosine 2 pi 0.5 t minus 90 degrees, or 1.5 sine 2 pi 0.5 t. Okay? So the current there, and so here's the voltage, here's the current over here. Those two things are in phase with each other. So the way I'm going to do that is I'm going to say, well, you know what? I'm going to say that my phasor is got a magnitude of 3, angle of minus 90, and now I'm going to calculate I. Okay? So I'm going to let that run. So notice that the vectors keep rotating. Okay, let me let that run all the way through. All right, a couple of things here. So what have I drawn here? So the red is the phasor V. So V, I'll write it over here, was 3 e to the minus j 90 degrees. Okay, so I can see that over here in the upper left. Okay, and I was half of that, right? It was 1.5 e to the minus j 90 degrees. And I can see it here as well. Okay, and notice what happened in the time domain. Right? In the time domain, the waveform that got traced out, both of them were sine waves, okay? And as time advances here, if I calculate I, so watch that guy rotating, right? At any given point in time again, so right now where I stopped this guy at t equal to 1.6, I can see that the real part of this guy is just below negative 3. In the time domain here, at the same time, t equal to 1.6, he's just below negative 3. If I run it a little further, let's say I stop right here, all right, time t equal to 2.6. At 2.6, the real part of this guy, the real part's down here on the real axis, just below 3. Right here on the time axis, I see at time 2.6, I'm just below 3 at the same point. Right? Again, the critical thing is that the static relationship, I only need to know the relationship between the phasors as they rotate. So the phasors rotate, but I only need to know the phase relationship at one point in time, right? The phase relationship doesn't change. The important thing is it doesn't matter whether or not I have a resistor or an inductor or any of that kind of thing, okay? And so we'll look at that in another video, but I first wanted to look at sort of that difference between sine and cosine and kind of relate those things. All right, so hopefully that helps to kind of understand that visualization. And I'll share this MATLAB with you so you can kind of play with it.